everyone. So welcome back to our second talk of the morning, and it's really great to have Mark Zhandry here of Stanford and NTT Research. Mark probably needs no introduction to anyone here. He has been a driving force of the intersection of quantum complexity and cryptography for the last decade, and he's going to tell us about how to model unitary oracles.
All right. Thank you for the introduction. Yeah, so this work was kind of a hodgepodge of a few different things that all kind of converged together. So there's going to be a lot of little parts to this talk, and I probably won't get through everything. And there's also things that I didn't even put in the talk that are in the paper, but that's fine. And then, please ask questions. I don't need to get through everything. Whatever is interesting, I'm happy to slow down and discuss some more. Okay, so there were a few things on my mind that have been on my mind for a while. So one is, what does it mean to, quote, efficiently implement a unitary? And informally, I think we all have an understanding of what this means, but it was actually only very recently, really, some notion of efficiently implementing unitaries was only recently formalized, 2 years ago. Another question is, how should we model query access to unitaries that are efficient? So we have some state, we want to apply some unitary to it, and we're going to model our unitary as some sort of oracle. Should we allow inverse queries? Should we allow controlling the unitary? Should we allow anything else? And then maybe the last question that was on my mind, and maybe a little, thinking about this a lot recently, is what does a black box unitary look like for the purposes of complexity theoretic or cryptographic separations? So imagine you have some cryptographic primitive, P, and you want to construct from it a cryptographic primitive Q. In crypto, we like to talk about black box constructions. From a practical perspective, they're more efficient, and from a theoretical perspective, it allows us to reason about the limitations of cryptography. So if you want to model a black box construction, we have this new primitive Q, and it's making queries to this primitive P. What should these queries look like? And actually, we can also do the same thing for an adversary. Most of the reductions in cryptography treat the adversary as a black box. So if you have, an adversary for Q, you want to get an adversary for P. That's how you justify that it's secure, because then you're violating the security of P. What does it mean for a black box adversary for P to make queries to the original adversary for Q? Okay, so these were the questions that were on my mind. And I don't necessarily have the final answers, but I have, some answers subject to further scrutiny. So one is that efficient implementation should mean a small circuit. That part's obvious. That implements U, including the global phase. So, normally we ignore global phase. And my stance, at least for the purposes of this talk, is that you shouldn't. You should at least pay attention to it when you're implementing a unitary. We'll discuss this more later. And then, I don't know if we'll have time, but ideally also you want to have your unitary have exponentially small error. Whereas normally we don't necessarily pay a whole lot of attention to, we care about the errors, but we don't often make a formal specification that, we really insist on exponentially small errors, but I'm going to make that claim. Okay, so then as far as how to treat oracles for unitaries, if the unitary is supposed to reflect some sort of some sort of efficient process, so oracles capturing efficient computation should allow controlling the unitary, should allow inverse and also controlling the inverse. This is relatively standard, nothing too out of the ordinary here. But then maybe the new part here is I also take the stance that you should allow conjugates and transposes, also control versions of those. Okay, and we'll discuss the reasons for those as well later. And then likewise, for black box separations, if you want kind of the best black box separation you can hope for, you really should also allow, your query modeling should allow controlling, inverses, conjugates, and transposes. Okay, so now I'll basically the rest of this talk, I'll be giving kind of a bunch of little results, little insights that support these claims. Okay. So let's start with the least controversial, which are controlled access and inverse. So this is, I wouldn't say they're universal. Definitely a lot of works don't pay attention to this, but it's pretty standard. You can definitely find it in the literature. So hopefully this isn't controversial. Yeah, and maybe the point is that these operations actually come up very frequently in quantum algorithms. Gentle measurement requires inverses. All these ones I've listed here require controlling, so doing the Hadamard test, which allows you to estimate the eigenvalues of a unitary, phase estimation, when you're doing amplitude amplification, if the angle is unknown, you end up doing some controlling stuff. In a more recent example, we have this quantum state repair technique that also requires controlling. Okay, so just from the perspective of trying to capture algorithmic techniques, it seems like it's important to handle controlling and also inverses. And why can we do this? Why can we control a circuit? Why can we take the inverse of a circuit? Well, it's because, well, let's start with the inverse. Well, just based on the basic rules of linear algebra, we can take inverses by inverting each gate and then just flipping the order. Right? Okay, so if we have a circuit that we can run in the forward direction, we can also run it backwards. And for controlling, we can actually likewise do the same, something similar. We can take each gate and just control that on whatever our control wire is. This one has been maybe like relatively folklore, but it was formalized in this somewhat recent work by Kim et al. And the point is, okay, so I now have these gates that are controlled versions of the original ones. Maybe they didn't come from the gate set that I was building my original circuit from, but because each gate is a finite-sized object, I can actually implement this gate just basically by brute force, Solovay-Kitaev kind of stuff, and I can implement these control gates with whatever universal gate set I want. Okay, but there is a caveat here that I think usually gets ignored, which is, okay, so strictly speaking, what you get out of this is that if you had your original quantum circuit Q, the unitary implemented by Q through this process of controlling each gate actually is the controlled version of the unitary implemented by Q, okay? However, when we say that a unitary realizes, or when we say that a quantum circuit Q realizes some unitary, we generally ignore global phase. And so actually, oftentimes what's happening is we have this unitary U, but Q, our circuit for implementing it, has some global phase term e to the I theta that we've brushed under the rug. Yes?
Like in the first step, though, you're making a choice of global phase for the gates, though, right, when you define this controlling operation, which is... Yeah,
okay, so yeah, if you're going to implement these from an underlying universal gate set, you might introduce a global phase. But if you're just going to take these as your gate set, then there's no problem, right? Then you are actually literally implementing the controlled version of that circuit. Okay, so fine, we have this global phase, but then what happens when I control is that the global phase becomes a relative phase between the first qubit being 0 and 1. And so when I control this circuit, I actually don't get the control unitary. Hopefully that makes sense. Okay, and yeah, and this is kind of inherent with the way we normally talk about quantum circuits and unitaries, because we're always ignoring this global phase. And if you ignore your global phase and you just do this naive thing, you end up you are not gonna actually implement the right unitary. Yes?
Can't we just always add a global phase? Is this ever an actual problem?
If you know what the global phase is. Yeah, so realistically, it never ends up being a problem, but you should be careful. So here's just one example just to show that this isn't crazy, that you should pay attention to this. Okay, so you'll just have to take my word for it. The determinant of the quantum Fourier transform is usually going to be 1. Or not usually. It's going to be 1 about a quarter of the time, and depends on the modulus you're doing the Fourier transform over. And in particular, in the commonly used case where the modulus is a power of 2, the determinant is actually not going to be 1. Okay. On the other hand, a very popular universal gate set is Clifford gates plus T gates. And if you have a circuit on n greater than or equal to 3 qubits that's made of Clifford and T gates, your determinant actually is going to be 1. Right? Basically, the Clifford and T, their determinants are all they're all powers of I. But then because you have the for any gate, you're not applying the gate on the whole entire set of qubits, and when you do that, you end up raising this I to high powers, and that's why for large enough qubits, you end up getting a determinant 1. And as a corollary of this, you actually can't implement the QFT exactly up to global phase, including global phase, with Clifford and T gates. Right? Unless you're in these 2 cases. But like for power of 2, you can't do it. And in particular, if you're going to try to implement Shor's algorithm, you're going to it's inherent that you're going to get a global phase if you're trying to implement Shor's algorithm in superposition using Clifford and T. Okay, and yes.
But the same thing happens to the QFT if you add and also the determinant becomes 1 in more cases.
It does, yeah.
So you could still implement Shor if you have an extra to it.
You might actually be right. Let me think. I mean, but if the extra ancilla is not really doing it, if you just have an ancilla and then don't actually touch it, it's not going to actually really change anything.
Sure.
So I
conceivably use them in some non-trivial.
You could, yeah, and you could potentially do that, but like the naive thing, you might run into issues because of this. Okay, and to make matters worse, there are actually families of unitaries that can be computed efficiently if you ignore global phase, but can't be computed at all when you pay attention to global phase, and also these unitaries can't be controlled. And the proof is pretty straightforward. Your unitary is just going to be the identity, except you're going to have a global phase term that encodes some incomputable problem, like the halting problem or something like that. So if you ignore global phase, this is just identity. It's trivial to implement. But if you're trying to force a global phase, or if you're going to control, then this global phase becomes a relative phase. And with the controlled version, you can actually learn the phase, which would allow you to solve the halting problem. So if you pay attention to global phase with this set of unitaries, then you actually just can't implement it. Okay. So the position that I take in this work is basically if we're going to talk about circuits efficiently implementing a unitary, so we're going to be kind of stuck because if we want to continue with the usual notion of a universal gate set, that's always going to create a global phase in certain situations. So we can't actually, with our favorite universal gate set, necessarily implement all unitaries, including global phase. But what we can do is actually we can actually just specify the global phase. So if we're trying to implement this unitary U, we implement it with a circuit. We'll generally actually know the relative phase between Q and U. And if you want to say that you've efficiently implemented U, you should be able to do this. You should be able to actually learn what the relative phase is and maybe write it down. Okay. And if you actually know the phase, if you know the global phase that your circuit added, then you can do this controlling, right? So I'm going to control each gate, just as I did before. Now, if I don't do anything else and I just leave it like this, we know that I might not be implementing the right unitary because there might have been a global phase here that became a relative phase here. But then I just correct for it by putting a phase gate. And because I know the phase, I can implement this. I know the phase that I need to add in the case for this qubit is 1. I can just implement this gate. Now doing so Doing this part might actually introduce a global phase, because again, my universal gate set might not actually be able to implement this gate up to global phase. But the usual methods we have of implementing gates from our favorite universal gate set, they actually will tell you what the global phase is. And especially because it's just, this is just a 2x2 matrix, so I can just look at it and figure out what my global phase is. And so then I just write down my new global phase. And then I can control again if I need to, or whatever it is. Okay, I wanted to mention just one other example. We're just, nothing, again, I hesitate to call this a bug in this work, but you just, you should be careful. So this Erhanov and et al. Work showing that you can estimate the Jones polynomial with a quantum circuit, they had this following blueprint where, I'm not going to talk about what the Jones polynomial is or anything like that, but the blueprint is you have this knot, you're trying to estimate something about it. You'll map that knot into a circuit, a Q, made of these unitaries UI. These unitaries don't come from any universal gate set, but the dimension of these unitaries is polynomial, they're on log qubits. And so what you do is you brute force each of these UIs to create a circuit for each UI, and then you stitch together all the circuits for the little circuits for your UIs to get your big circuit Q. Then you do this Hadamard test thing where you estimate the eigenvalues, or not the eigenvalues, but you estimate this quantity for a given state. And then this gives you the approximation that you're asking for. But for this step, where you're doing this Hadamard test, you actually need the controlled version of the big unitary, which mean, and which they just say like, oh, well, you can control the big unitary by controlling each gate of Q. But the process of implementing these UIs from your universal gate set may have created a global phase. So if you're not careful, then controlling Q is actually going to give you the wrong answer. Okay. So this is my point with this is just that you have to be careful. It turns out that it's really not hard to deal with. You can either deal with it generically, like I said before, where you actually know the global phase introduced by these guys, and so you can control by, once you know the global phase, you can actually control. Or actually, you can actually just directly implement the controlled versions of these UIs, because you're just brute forcing them anyway. The controlled version just doubles the dimension. You can brute force these as well. So it's not really a problem, but you should be careful. Okay, so hopefully nothing I've said so far was all that controversial. But now I'm going to get into the new stuff, which is what about conjugates and transposes? Okay, so first, the observation is that we can implement conjugates and transposes basically the same way that we implemented inverses and controlling, where you just take the operation and you apply it gate by gate. So for conjugate, you just conjugate each gate. Maybe this moved you out of your universal gate set, but you can correct for that by standard techniques. And then for transpose, you just transpose each gate and then reverse their order. All right, so these are things that we know how to compute efficiently. If you have an efficient circuit for U, you can efficiently compute the circuit for U star, U transpose. And I guess what I want to do now is justify that, where this might come up to really, justify my claim that you should model your efficient access to unitaries in this way, and you shouldn't ignore them. And I'll be focusing on black box separations. Okay, so what is a black box separation? Basically, because of the current state of complexity theory, we often cannot prove that, say, a complexity class is actually hard, or we cannot prove unconditionally that some crypto primitive is impossible to build from another one. But we nevertheless want to justify why this seems to be the case, why it seems like this complexity class is harder, why we can't build a crypto primitive from another one. And the typical solution when we want to do something like this is to use an oracle separation or black box separation. And a famous example from the quantum space is Aronson and Kuperberg showed that QMA and QCMA are different relative to a particular unitary oracle U. Okay, and this is some heuristic evidence that maybe these complexity classes are in fact different. And it helps us understand why some things might be hard. And the intuitive justification is that oftentimes the best we can do with a quantum circuit is just evaluate it on certain inputs. And what these black box separations are doing is they're really kind of like enforcing that. They're just saying, okay, well, often all we can do is evaluate it, so we're just gonna say that is all you can do. You can't do anything but evaluate it and then see what happens when we do that. Okay, but there's a natural question, which is how reasonable are black box separations? And we know that they can't reflect the real world in general. There are some known failures, IP versus p-space being one. We know that they are the same, but relative to a random oracle, they're different. So we know that the statements that you can get from query complexity will sometimes be wrong. But nevertheless, it seems to be a reasonable heuristic and is widely used throughout both classical and quantum complexity theory and cryptography. But what this says is that, okay, we want to use these heuristics, but we want our heuristics to be kind of as close to the real world as we can reasonably get while still being able to make interesting statements. And so we want, however we're modeling our oracle axis, we want it to be as close as we can get to the real world. And so our thesis from this perspective is that if you really want to get your unitary oracles to be as close to the real world as you can get, you should really implement them, or you should really enable the adversary to query the conjugates and transpose, and also the controlled and inverse versions. And the reason is because we can do this on a real circuit, you should be able to do this when you're modeling the circuit as an oracle. Yeah.
Mark, if you're trying to provoke people into arguing with it, right? So certainly, Greg and I talked about this 20 years ago when we were first using quantum oracles, right?
Mm-hmm.
Should we include controlled U? Should we include U dagger? I don't remember how much we talked about U transpose and U conjugate. Mm-hmm. But the problem, for me, the problem is not should we include those? Yes. If you can, then that's all the better. But it's how do we know that this is the complete list?
We'll get to that later.
All right.
Yes, I have a section on that.
All right.
Okay. So so that was kind of like an informal, intuitive take that we want to get as close as we can to the real world. Now I'm going to give you a bit more of a concrete example of why we should model things this way. Okay, so again, Ernst-Kuperberg, they showed that QMA and QCMA are separated relative to some unitary oracle U. And there have been tons of other separations in the literature. I just didn't bother listing them. However, for a variety of reasons, unitary oracle separations are considered non-standard. I mean, I think they were considered very non-standard in 07. Maybe they're more standard now. But we still like to say that it's better to have a classical oracle separation. Some reasons for that are, well, we are usually talking about problems with classical input, classical output. If you're throwing a unitary in there, you're kind of changing it into a quantum input, a quantum output problem. So intuitively, it seems like you've moved away from what you're trying to show. For cryptography, you might be able to heuristically instantiate a classical oracle using various crypto tools, whereas a unitary oracle might be harder. So there's a number of reasons why we might want a classical oracle separation as opposed to a quantum one, and this has been kind of a notable research goal over the last 15 years, is to try to move from unitary separations to classical ones. Okay, so this brings up a natural question. Can you implement the Ernst-Kuperberg oracle using a classical oracle instead? A version of this question actually appeared in their work, which is now known as the unitary synthesis problem. But I guess what I wanted to point out is that, first thing I wanted to point out is that you actually have to be careful about exactly what you mean when you say implementing the Ernst-Kuperberg oracle. So, the first thing you might say is that, okay, I have this Ernst-Kuperberg oracle. I want a quantum circuit that makes queries to some classical oracle that basically implements this U, or maybe it's indistinguishable from this U if you're query bounded. So that's a natural first attempt, but it turns out that this really probably is not good enough. And in particular, we actually, we actually now know that you can implement this U from a classical oracle, but it's not in a way that actually gives you a classical oracle separation. And the reason is that your algorithm, your supposed Q, in their case, QCMA verifier, or for crypto, your adversary, whatever, your algorithm isn't restricted to just querying Q to the O. Right? The algorithm actually can just query O directly. And this O, direct access to O, may reveal a lot more information about the unitary U than the adversary is supposed to learn. And that might allow them to break something where, given just U, they're not able to break. So we actually, in cryptography, we know how to deal with this. We've known for a while. And what you want is something that we call indifferentiability, which is where you actually allow the adversary to query both Q to the O and O. This is called we'll call this the real world. And then in this other world where the left oracle is the ideal unitary, you need to somehow get an O to answer the adversary's O queries. And what we ask for is that you can simulate O. So in this case, you have this Q making queries to O, and the adversary can query both of these. On the right-hand side, you have a simulator making queries to U, and the adversary can query both of these. And we call this the ideal world. All right, and it turns out that this is good enough for most settings in cryptography, at least. This is a kind of a well understood thing in cryptography. There are some places where it fails, but for most of the things we care about, if you can have an indifferentiable oracle construction, actually everything will work, and you can lift your separations from U to O, and we're all happy. Sometimes we know it fails. I haven't thought a whole lot about what happens for complexity theory. I think if your complexity classes are efficient, I think this should also work. Weird things happen though when you have witnesses. You have to somehow model your witness in this notion. So for inefficient classes like QCMA, even indifferentiability is not going to be enough. But at least, this is kind of outside of the theme of this paper, but I did want to mention this. It's an interesting question. So like a very natural question, and maybe progress towards getting moving the Aronson-Kuperberg separation to a classical oracle would be, can you implement their oracle from a classical one under the strong indifferentiability notion? Okay. Right. That's. Oh yes, question.
For the weak notion in differentiability, what was the construction of
I mean, you can do state synthesis from a classical oracle, and once you can construct the state, you can reflect around it.
I think we basically just said, like, we'll be happy with any mock-up of our quantum oracle using a classical oracle that is good enough to prove the desired oracle.
Yeah. Okay, so on one hand, differentiability is too strong and too weak, right? It's too weak because it doesn't handle witnesses, but it's also maybe bigger than you need, because the indifferentiability literally says you can use it anywhere that the composition theorems are valid. Maybe for QMA and QCMA, you don't need to go all the way to indifferentiability.
Yeah.
Okay, so can we implement quantum oracles using a classical oracle under indifferentiability? And the theorem we've proven this work is no, unless your quantum oracle allows U dagger, U star, U transpose. There's some annoying reasons why we can't handle controlling with this, but okay, so ignore that part. But if you want to build a quantum oracle from a classical oracle with this strong indifferentiability notion, you really need to model your quantum oracle as allowing dagger, star, and transpose. And the proof is a little annoying, and there's caveats, but here's the rough intuition. Okay, so let's look here, and let's pretend I didn't have the stars, the conjugate here. So this is just the proof for conjugate. So just based on indifferentiability, we have this simulator that can make queries to U and simulates the random oracle. And now I can imagine running my quantum circuit Q, making queries to that random oracle. And the indifferentiability guarantee is that this thing actually just implements U, or looks like U. Okay, so I have U is indistinguishable from Q to the sim to the U. And then I just star both sides. That's fine. Nothing interesting happens there. And now I imagine taking this whole circuit and I conjugate it. Well, I can conjugate each gate, each non-oracle gate in Q. And then I can also conjugate the query gates. That's what this represents here. But now, sim, remember, is simulating a classical oracle. Well, the conjugate of a classical oracle is just itself. So the star actually goes away. And I'm left with Q star. So this is Q, where every non-oracle gate is conjugated, making queries to simu, where this simu is actually classical, or not classical, but not conjugated. And what did I just show? I showed that by chaining these together, I am able to implement U star on the left by making queries to U. Right, so just the fact that I have this indifferentiable construction with the simulator says that I can actually take the simulator and the circuit and use it to actually implement the controlled version of U from U itself. So I might as well give you access, since you can do it for yourself, I might as well give you access to U star in the first place.
Sorry, what is this sim? You said it's a classical?
It's simulating a classical oracle, right? Because I'm building a quantum oracle from a classical oracle.
So is sim?
Sim is not classical. Sim is quantum. It's making quantum queries to you.
That makes queries to you.
Yeah, but it's trying to look like a classical oracle, right? That's the guarantee of indifferentiability, right? I have some construction of a quantum circuit making queries to a classical oracle, and the simulator has to look like it's actually simulating that classical oracle. Yes.
Sorry, when you say it simulates a classical oracle, it's going to answer the same. If I queried X,
yeah,
you've answered the same thing.
Yeah.
But how do you enforce this?
I mean, I don't. For this purpose, I don't care, right? If you want, maybe this could be a very, very hard problem.
I see.
I'm just saying, if you had this, what are the consequences of having this? If you had an indifferentiable construction of a quantum oracle from a classical oracle, you need a simulator. Again, I don't care how you came up with it. Maybe it's really hard. Maybe it's actually impossible. I have no idea. But if you gave me a simulator that actually simulated this classical oracle correctly, then I can turn it into an efficient query algorithm that makes queries to U and implements U star. Right? Okay, yes?
Is it then basically fair to say that simu is just a permutation unitary? Like it just permutes the basis states because it's just the classical?
Yeah, I mean, we don't actually know. So sim could be keeping quantum state, and it could be like looking at the queries you queried and making sure that if you query the same thing twice, it's consistent. But if you don't query the same thing twice, it does something completely bonkers. We don't know. So you have to, like, the proof actually is a little delicate because we don't know what sim is actually doing. But you can show something kind of intuitively like this. And again, I said there's caveats. I'm actually only implementing U star in kind of an average case sense, so you could have like particular states where it fails. So there's a lot of caveats, but this is kind of the moral of this theorem, is that you can implement U star from U, and so you might as well just model it in your query.
But this still doesn't rule out that under indifferentiability I could get more than just these three.
I'm getting there. I'm getting there. Okay. Yeah, so I just wanted to mention, okay, so this is still relatively abstract. I wanted to mention one concrete application of this theorem, which is kind of an interesting question that came up since last year. So now we know how to build, due to Ma and Huang, we know how to build pseudo-random unitaries from pseudo-random functions. And a natural question is, does this give you some way to actually implement a random unitary from a random function? Okay, so what do they show? They show that if you have a random permutation, random permutation oracle, a random phase oracle, and then you nest it between two independent Cliffords, that the circuit you get is indistinguishable from a Haar random unitary, even up to inverse queries. Right, and then to get a pseudo-random unitary, you would implement the permutation and phase oracle with a pseudo-random function to actually make it efficient. But I'm just going to start with kind of this theorem. And the natural question is, does this actually allow you to build a random unit, right, so we're saying, this gives you this indistinguishability notion, right? It says, if I just give you access to you or this construction here, you can't tell which world you're in. And now I'm asking, can we get the stronger thing? Can we get this indifferentiability notion where I actually can simulate, I have a simulator that makes queries to you and actually correctly simulates the PNF functions. And if you could do this, I think this would be really cool. I have no idea how to show anything like this, but I think it'd be really cool if you could do that, because then what it would allow you to do is that you could take anything that you're willing to model as a random function, and you could actually construct from this a random unitary. And random unitaries, at least, they seem like a natural object. They've been used in cryptography recently for various things. There might be some complexity theoretic separations using random unitaries. I think there are. I think this would be a very natural question. And the key takeaway, though, is that if you wanted any hope of doing this, if you wanted any hope of building a random unitary that was indifferentiable from random functions, you need to enable query access to all these things. Conjugates, transposes, inverse. I don't know what to call this. Star security or something. I don't know. For just modeling query access to these, we call it strong. This is weak. So maybe star for everything.
Arguing that this should just be the definition of PRU and it's not achieved yet?
I don't know. Not necessarily. I think for PRU, like for cryptographic applications, you potentially have a lot of control over what access you give if someone's querying you, right? And in the classical world, we have the same kind of thing with PRPs, where you could either just allow forward or inverse. In some applications, forward's okay. Some you really need both. So I think for PRUs, it really depends. But if you wanted to go to this unitary that everyone can access, where it's not me with my secret key evaluating it, you really do need to model all of these things. And this attack is actually different than the one in the paper. It turns out it's relative. There's kind of direct ways to attack their scheme for indifferentiability. But what I wanted to show here is that a special case of their scheme, one that they didn't analyze, so I'm not contradicting anything in their work, and it's obviously also a different security model, kind of looking at star security, which they didn't consider. But in their scheme, when the phase is actually just binary phase, it can't satisfy the star security notion. And here's why. Basically, U star. So I'm giving you access to U star in addition to U. If I take the conjugate of CFP C prime, well, these are actually P and F are just classical. The real valued unitaries. So star doesn't affect them, and so I get C star PF C prime star. And then it turns out that this is a fact about Clifford's, that C and C star just differ by applying polys. And so what you actually get is that U star is the same as U, except I've acted on by polys. Now I don't know what these polys are, but I've just acted on by some polys. And now the point is that you can actually learn these polys, and that gives you your distinguishing attack. So suppose for the moment that we actually only had X gates on either side. This is just an instance of Simon's oracle. I mean, it looks a little different because it's a unitary and not like a classical function, but morally it's the same thing. So this is an instance of Simon's oracle, and so we can find these shifts theta and theta prime just with polynomially many queries. And then once you have theta and theta prime, you can strip these off, and you can easily distinguish in that case. You can likewise handle the case where these are just z's, because z's are just x's in a different basis. So you can also do. And then you can actually combine the x's and z's. You have to be a little careful because x's and z's don't commute. So strictly speaking, if I have the full thing where I have x to the theta z to the phi, it's not strictly speaking an instance of Simon's oracle because the x's and z's don't commute. So I'm not exactly just shifting. However, even though x's and z's don't commute, the tensor with themselves does, right? Because when you commute, you just pick up a minus sign. So if you do it twice, you cancel out. And what that means is you can basically make two queries to to U, 2 queries to U star, and you actually do get a Simon's oracle if you could just kind of like take the tensor product of U with itself and U star with itself. And that allows you to, then you get a Simon's oracle, and then you can compute these shifts. And there's also, technically we need a controlled access to U and U star to implement Simon's. That's not a big limitation. One of my points here was to say you need controlled, but technically the indifferentiability theorem doesn't give you controlled. But you can actually get around this by using some more tricks. Basically, instead of controlled being whether you evaluate U or whether you don't evaluate it, you can just always evaluate U star, and just switch which state you apply it to. And then you don't need control. So anyway, when the phase is binary, their construction is not star secure. I don't know if it's star secure when they move to higher arity in their phase unitary. It might be, might not be. I'm not sure. Okay. Let me pause for questions. Okay, now Scott, you need to pay attention because we're getting to your question. Okay, so natural question is, okay, I said we can do controlled, we can do inverse, star, transpose. Why stop here? Why can't I do anything else? And here's a justification for stopping at these things. So first, notice that the exact reason why we can implement controlled and conjugates are because they're homomorphisms on unitaries, right? So if I control UV, that's the same as controlling U and then multiplying by control V, and same for conjugates. Transpose and conjugate transpose are what are known as anti-homomorphisms. It's basically the same thing, but when you break it out, you just reverse the order of the computation. And all anti-homomorphisms are just the inverse of some homomorphism. And so really what we should be caring about are homomorphisms, right? So the question is, are there any homomorphisms outside of controlled and conjugate that you can apply? And and then by inverting them, we can talk about some anti-homomorphisms. Okay, so if I gave you any homomorphism or any anti-homomorphism that you could compute efficiently on the gates, then you can compute them on your favorite unitary just by applying it gate by gate. So the question is, what homomorphisms can be efficiently computed? Well, let me start with an interesting example of the determinant. This is a homomorphism on unitaries. Well, actually, if I give you a circuit Q, you can take the determinant of that circuit by taking the determinant gate by gate. Okay. Okay, so this might look like, actually there is more. You can do determinants, and that's something that's not controlling or conjugate, so maybe there is more that you can do. However, it turns out that this naively doesn't work, and it's because it's ignoring ancillas. And when you pay attention to ancillas, then actually determinant becomes hard. Okay, so in general, when computing a unitary U using a circuit Q, Q may use ancillas. I think most of the circuits that we think about actually use ancillas. And so just here will be my model of ancillas. You can imagine different models, but this is a natural one. So typically ancillas are initialized to 0. And then at the end of the computation, they return to 0. This isn't really important. Oftentimes we just throw stuff away, but usually when we throw it away, we actually know what the state is. And so you could always return to 0 with a little bit more work. So this isn't really without loss of generality, and everything I'm going to say actually works even if we replace 0 with some other state. So typically our quantum circuits actually look like this. We have this unitary we're trying to evaluate on our state psi, but our circuit actually has a 0, and it returns to 0. Okay, and if we were to write this unitary as a matrix, the unitary implemented by our circuit would look like this. These things here are 0, and that corresponds to the fact that I'm starting from 0 and returning to 0. So there's no cross terms here. So for the basis states that have a 0 in the end, I am actually implementing u. And then for everything else, I'm implementing something else, v. And this could really, it just depends on the circuit. It could be arbitrarily related to u. There's no reason for this v to have any relation with u. Now, when I take the determinant of the circuit q, I'm actually going to get the determinant of u times the determinant of v. So I get the determinant of u here, but because I'm kind of scrambling it with this determinant of v, and this determinant of v could be anything. And so what this means is that taking the determinant of my circuit with ancillas is actually arbitrarily related to the determinant of u, and I don't learn anything. Maybe a more concrete way to look at this is, going back to earlier in the talk, we know that Clifford plus T circuits are generally going to have determinant 1, even though they're implementing circuits that may have interesting determinants. So, at least naively, we know that there's no way to compute the determinant of u. And we can actually prove that you can't do this efficiently. So this is maybe getting a little into the weeds here. But let's suppose, okay, we know we can't go gate by gate to compute the determinant. But maybe there's some other process that actually does compute the determinant, some other homomorphism that we can evaluate that effectively gives us the determinant. And that would roughly look like this. So I want some homomorphism that I'm applying to my unitary, to my circuit. Now my circuit has ancilla, so it has this v. But somehow the homomorphism behaves in a way that what I get here is exactly my desired. So think of H as determinant, right? I actually get determinant here, and I get some other junk here. I don't even know what it's going to look like. That depends on U and V. I don't care what this is, but what I care about is if I give you a matrix of this form, that I actually get, say, the determinant or whatever my favorite homomorphism is here. Okay, so I'm going to call this an ancilla respecting implementation. And what it says is that, right, so this is a circuit with ancillas, and I can compute this thing by initializing some 0 ancillas, and it will actually return them to 0. So this is like, this preserves the ancilla structure of the unitary and actually computes the homomorphism I want. And you can just convince yourself that controlling and conjugate actually have such an implementation. Really, it's just itself. It is its own implementation, its own ancilla respecting implementation. And now the question is, can we do determinants? And the short answer is no. So let's let H be some continuous homomorphism. Then either we can implement H by polynomially many queries to controlled U or controlled U star, or there's no efficient ancilla respecting implementation. Any ancilla respecting implementation will necessarily be inefficient. Okay? And so this really says that really all I have to care about is controlled U and control U star, or making polynomially many queries to them. And I'm just going to do the proof for determinant because it's the easiest to see. I hope I have enough time to get through it. It's not too hard, but it'll take a few slides. So suppose I had, okay, so I want to compute determinants, including ancillas. So suppose I had an ancilla respecting implementation det prime. I'm going to let W be some diagonal matrix with entries di, and think of these as like formal variables. And, you would actually set them to be concrete things, but think of them as formal variables. And let's let pi be some permutation matrix, of the same dimension as W. All right. So since W is diagonal, if I apply this permutation matrix to the left and the right, I'm just scrambling the diagonal entries, and I'm still going to get a diagonal matrix here. And I'll just break it up, break this diagonal matrix into into two pieces, W pi and then V pi, which is just junk I'm going to ignore. Okay. So I have this so I'm imagine fixing W as this thing containing these formal variables on the polynomial, and then imagine applying different permutations pi to W. I'm always going to get a structure that looks like this. And now because I have this hypothetical ancilla respecting determinant, well, what does ancilla respecting mean? It means I'm exactly, when I apply this homomorphism to this unitary, I'm exactly going to get det the determinant of W pi here, and some junk here I don't care about. All right? But also, that prime is some homomorphism that I'm applying, gate by gate, let's say. I don't care, but it's some homomorphism. And what that means is I can actually pull the pi's out, right? I can pull pi out on the left, pull pi out on the right. And remember that, so det prime is not a scalar, so these things don't necessarily commute, but this, this still works just because det prime is a homomorphism. So what I get is that I can actually arrive at this matrix here, and in particular, the determinant of W pi, by first computing det prime of W, and then applying these det prime of pi's to the left and the right. Okay, now here's the next thing. So let's imagine I fix pi. So this is just then a matrix. This is just a matrix. And so the product of these is actually a linear combination of the entries in det prime of W. And in particular, det of W pi is a linear combination of the entries of det prime of W. Okay, and now we're basically done. So remember I said that, that W was just this diagonal matrix. I'm treating everything as kind of like a formal variable. And now, what is the determinant of W pi? Well, W pi, I just scrambled the entries in some way according to pi. Some of them are going to be in this initial segment, the rest are going to be outside. And then the determinant is just the product of the diagonal entries. So det W pi is just the product of some subset of my diagonal entries. And by varying pi, I can actually get any subset I want here. So for any subset that I want of the diagonal entries, I can put that subset in the upper left corner, and by choosing pi appropriately, and I can talk about, and then I can take the determinant to get the product of those things. Oops. And so the point is that let's suppose that my W is a unitary on n qubits. So that means its dimension is 2 to the n. But now let's even say I have 1 ancilla qubit, right? So the unitary I'm trying to talk about is n qubits, but W is going to have an ancilla, so it's really n plus 1 qubits. So if I look at the possible values for the determinant of W pi, there's going to be, I worked it out here, right? It's going to be 2 to the n plus 1. Choose 2 to the n possible subsets of the entries in W. And so the dimension spanned by these products is actually something like 2 to the n, double the exponential. All right, and what that means is, remember, all of these things here are linear combinations of the entries in my matrix, and yet they span a space of dimension 2 to the, they span a space of dimension 2 to the n. And what this means is, because I'm taking, just by linear algebra, right, my matrix det prime of W it just exists in some vector space. And somehow, by taking linear combinations, I'm able to span a space of dimension 2 to the n. So that means det prime of W needs to span a space of dimension 2 to the n. So I need at least 2 to the n entries in W. So that means it's still basically 2 to the n. There's a minus over 2 in the exponent, fine. Its dimensions need to be 2 to the 2 to the n over 2 by 2 to the n over 2. And basically what that means is, if you talk about in qubits, it means that the det prime of W unitary has to be unitary on 2 to the n minus 1 qubits. But that's exponential, so I can't even, I have no hope of even implementing this just because it's an exponential number of qubits. Okay, so I know I went relatively fast over that, but the point is that in order to implement these homomorphisms in a way that respects the ancillas and actually gives you a meaningful thing even if your unitary uses ancillas, if you can't be done by a polynomial number of queries to Cu and Cu star, you're going to end up, your homomorphism is going to spit out things that involve exponentially many qubits, and therefore just can't be efficient.
Where did you use the det is continuous?
So I didn't use, this is a proof by example. So det is continuous, I didn't use that fact. The general proof says any unitary, or sorry, any homomorphism on unitaries that is continuous, I can use the representation theory of unitary homomorphisms to kind of decompose it into some operations. And those operations basically will make some number of queries to CU. If they make more than a polynomial number of queries to CU, you're going to end up with the same phenomenon happening. Yeah, but the determinant is just one example. I mean, it happens to be continuous, so it's the theorem statement's more general.
I see. So as soon as you started talking about this, I started thinking of what would be an example of a homomorphism on oracles that would not be captured by this, right? And so one that I've thought about is algebraization, right? Where you just take your oracle function and you lift it over, lift it to a larger field, right? That's a different thing that you can, that if you had this oracle, if you had the implementation of this oracle by gates, then you would also have access to that larger thing, right?
Yes.
Which is not captured by this.
It is not.
On the other hand, that's not a continuous homomorphism.
It's not a homomorphism either.
It's not?
No.
I think in some sense it is, because you can lift if you think of it as like operations like and or and not, then and those are getting lifted to
I don't think so. I think you can basically end up with situations where you have gates that commute, but when you arithmetize them or algebraize them, they don't end up commuting. So I don't think it's something, but it's not a homomorphism.
I see.
I'm pretty sure.
I see. So it's some kind of lifting that falls short of being a homomorphism in the relevant sense.
Right. So the takeaway is that if you want to move beyond control U star, and then their inverses, you need to move away from homomorphisms. You need to move to something like algebraization, or I don't know, something else. And we know that you can do things with circuits that you can't do with these oracles. And the question is where do you stop? How far do you insist on going? And I think this is a reasonable stopping point. It's clearly not the best we can do, but it's a reasonable stopping point because basically any homomorphism is going to be captured by control. If you're talking about ancillas.
Any continuous homomorphism.
Any continuous, okay, yeah, fine. Any continuous homomorphism. I don't know what a non-continuous homomorphism would look like, or even if you could do it efficiently.
Okay, so you don't have any examples that are not continuous.
I don't. I'm sure someone out there does. I'm not a representation theory expert or anything like that, so I'm not sure. But I think they do exist. So I'm out of time. There are a few interesting kind of other things that I would have talked about if I had time. I'll just briefly mention. So this fact that if you don't have ancillas, you can compute determinant, but you can't compute determinant if you have ancillas, kind of leads to a natural question about ancilla complexity. I'm not the first to talk about ancilla complexity, but one interesting thing that came out of this, I won't give the proof, but we can actually come up with a family of quantum circuits that you can compute efficiently with 2 ancillas, but you can't compute efficiently with 0 ancillas under a purely classical complexity theoretic conjecture. So I thought that was kind of cute that you can get this quantum separation from a purely classical separation. And then I didn't talk about the error model, but basically, at least for crypto purposes, if you don't insist on at least negligible errors, you can actually run into some issues. This one I'm kind of the least confident about. I don't know if our error model is the right one, or if there's something better. Maybe there's no just one-size-fits-all error model. But I think there's an interesting question of exactly how close you should insist on getting your unitaries to the thing, your circuits to the unitary you're trying to compute. And with that, I will stop. Thank you.
Great. Questions for Mark?
Yeah.
So I'm a bit confused about your proof. You kind of prove unconditionally that some operation cannot be done efficiently.
Yes.
How can you do that?
So so it just says if your homomorphism is continuous, or let's just talk about determinant, right? If you want a homomorphism that effectively computes the determinant, even for circuits that have ancillas, it just says that you must have this exponential blowup in the number of qubits of your circuit, and there's no like hard complexity theoretic barrier to showing a lower bound on the number of qubits.
Right. So
Also,
at some point,
you have to implement it in the fashion of a homomorphism, which is an additional constraint.
Yes. Yeah. So I'm insisting that your determinant, the thing that's implementing the determinant, is itself a homomorphism that uses ancillas. And I'm just saying, well, you're going to need an exponential number of ancilla qubits.
and basically it's like a counting argument on all these different. But you're using like every permutation, right? And
Yes.
circuits for those.
So I'm using every permutation in order to do this like dimension counting thing. Yeah.
The circuits for those permutations are not going to be efficient.
It doesn't matter. Right.
Maybe I'll read the paper. Still,
Right. It's just a lower bound on qubits. Right. So it doesn't matter that the
To me, the worry is that this lower bound is coming because you're having to compute this on these permutations, which are huge themselves. So
But it's just a homomorphism, right? So you can always, right, I'm insisting on this mathematical structure that it's a homomorphism.
so you can reply it gate by gate.
And you can apply gate. Now, I mean, the counting argument requires me to go over all possible permutations. I guess, some permutations will have big circuits. But again, it really doesn't matter. I'm not using anything about, I'm not really using anything about the gate complexity. It's really just the dimension.
By the way, is the paper out?
Yes.
So you show that the determinant it's not like efficiently ancilla respecting.
Yeah.
Do you have any other examples like that aren't the determinant for
That we can compute without ancillas?
for homomorphism that is not like an efficiently ancilla respecting? Or whatever you call it.
I mean, for example, computing. So, I can just talk about this tensor product with itself a super polynomial number of times, or something like that. Would be an example. That's kind of like trivially inefficient, I guess. Yeah, and you can get sort of interesting non-trivial homomorphisms if you say like take U, tensor it with itself, but then project onto the symmetric subspace, right? So that's like writing that unitary down looks non-trivial. It's not a tensor product anymore, but you can still implement it with just two queries, right? Because it's just it's just you acting twice on the symmetric subspace, and basically the representation theory tells you that any continuous homomorphism can more intuitively be decomposed into some invariant subspace, and then just acting on the different components of that subspace by making queries to U. So determinant is also an example of this. There's like a highly antisymmetric subspace. You just apply U. It's exponentially big, and you just apply U component-wise to each entry of the subspace. And basically, that covers everything if you're restricted to continuous homomorphisms. Does that answer your question? Okay. Yeah, Eli?
Just to follow up to Peter's question, do you allow, I guess, cryptographic implementation of determinants, determinant that would only be correct on efficiently findable lists?
Yeah, that's a good question. So I'm insisting that you're like exactly implementing the homomorphism. It would be interesting to see if by allowing like a little bit of error or something. I'm not sure if efficiently findable. Yeah, I don't know. Possibly that would be another way out, is if you allowed some error or restricted in some way, rather than this really strong condition that you're exactly implementing this unitary. Yeah.
So, sorry, maybe you addressed it was a few minutes late, but so this oracle by William relative to which like P is equal to MP, but was it a quantum oracle?
Yes.
And if it's a quantum oracle, do your results shatter it out in it? So will it extend if you have those aberrators?
That's a good question. I don't know the answer. My guess is that everything's fine if you do allow conjugates and transposes. But that would need to be double checked.
Also, you didn't address it.
I didn't address it, no.
To me, that would be the most important question from your talk.
Yeah, I mean, I expect that it works.
Yeah, I think it's fine too.
Yeah.
Mostly just because it's fundamentally a concentration of measure thing.
Mm-hmm.
For the quantum separation, that I think that concentration of measure result holds too for the transpose and the inverse.
Yeah. Sounds believable.
Do you have some additional argument for why like anti-homomorphisms are the only thing you need to consider besides homomorphisms themselves?
Not really, no. Just at the very simple, just reverse the gates, right? I mean, again, you know, there could be a whole wide world of things out there beyond homomorphisms.
Yeah.
But they're at least of a different flavor than the normal things that we think about, like controlling and.
Right. I know that like the physicists have these classification theorems, like everything has to be either unitary or else anti-unitary. I forget under what condition, but like, I'm wondering if there's a connection to that.
I don't.
Okay.
So like if the implementation of unitary is allowed to use the quantum circuit and the auxiliary states, then like a recent work by myself and Miriam actually like achieve indifferentiability and with negligible error. So I was wondering like what's the advantage of using a gate implementation of a unitary rather than the like gate plus some state?
Well, I mean, I guess the question is, where does the state come from?
Like prepared by someone that produces the implementation.
Yeah, I mean, it's an interesting question to think about what happens if you're allowing quantum states, but I guess from my perspective, at least as like a cryptographer, how do we communicate what circuits to use and stuff like that? We just post it online or something like that. And you can't post these quantum states online, and I'm not sure if they're efficiently preparable, and by whom.
I prepare an implementation and like give it to you, and you can run it to implement you.
Mm-hmm.
But you don't know like how the state is being prepared, so you can only run it, but you cannot prepare it.
And what happens if I don't know, but I think things get a lot more delicate when you're allowing quantum states. What if it's not prepared correctly? Who prepares it? How do you transmit it? But yeah, it's certainly something that would be interesting, and that would probably avoid my results here, because that quantum state, if you're not allowed access to the conjugate of that, then you probably can't conjugate.
All right. Well, it's great that there's so much discussion. We should continue it over lunch. Thank you again, Mark. I believe we reconvene at 2, and Ewan will be speaking.